So I'm going to do a few calculations related to spontaneity and delta G with regard to this reaction that's written at the top of the page here. And you have delta H and delta S of reaction listed here, but you might not. You might have to calculate them using delta H's of formation or entropies, standard molar entropies. You know how to do that. You use Hess's law to do that, and you look up the reactants and products and subtract the reactants from the products. And you make sure to use the coefficients of the chemical equation. So I did that in another pencast. In this pencast, we're just going to take those as given, and we're going to use them in these calculations for delta G. And so the first question is, what is delta G at these two different temperatures? So let's look at our equation for delta G. Delta G equals delta H minus T delta S. And before I plug in any numbers, I'm going to analyze this and come up with a prediction of under what conditions my reaction is going to be spontaneous or not spontaneous, if any. I have two positive values here. My delta H is positive and my delta S is positive. Okay, so if I go and look at what a positive delta H and delta S do in my equation, basically what it does is it makes this delta H positive, of course, but then this whole negative T delta S term becomes negative because we only, in the Kelvin scale, we only have positive values for temperature. Okay, so that has to be positive. And then the delta S is positive. And so if you take two positive numbers, multiply them together, and put a negative sign in front, then that whole term is negative. So what that means is that in order for this reaction to be spontaneous, this T delta S term is going to have to be big enough to outweigh the positive delta H, and therefore give a negative delta G, because we're looking for a negative delta G for the reaction to be spontaneous. So my prediction would be that at low temperatures, this negative T delta S term is going to be too small to outweigh the delta H, and delta G is going to be positive, and the reaction is non-spontaneous. But at some temperature, some higher temperature, somewhere up there, we don't know what it is yet, it's going to switch, and it's going to make this term, this negative T delta S term, big enough to outweigh the delta H and make the whole reaction negative, or make the whole delta G negative and make the whole reaction spontaneous. So let's do the calculation at these two different temperatures. First, the 298, we're just going to plug in our values here. And at 298, that's what the standard conditions are, and that's the temperature at which these delta H's and delta S's are reported usually. You can tell that by this little degree sign up at the top. Okay, and by the way, we can put it here too. And so we're going to subtract that 298K times the delta S. And you've got to be careful because delta S's are usually reported in joules, not kilojoules. So I usually find it easier to convert from joules to kilojoules than the other way around, just not as many digits to write down on my piece of paper. So 0.159 kilojoules, I'm dividing by 1,000 over Kelvin per mole. And that is going to give me 131 kilojoules per mole. It's a positive value, just like we predicted. It's not a big enough temperature to outweigh the delta H, the positive delta H, and so it's going to be an overall positive delta G in a non-spontaneous reaction. Now let's do that for our higher temperature. We'll see if it's high enough to outweigh the positive delta H. We're going to use our same delta H and delta S. Even though delta H and delta S can change at different temperatures, we are going to assume that they're stable enough under these conditions in order to use them. And you will always know in a problem on an exam or in a textbook, or at least on the exams that I write, you'll always know whether these delta H's and delta S's can be assumed to be the same, relatively the same, over the temperature range of interest. So that means that we're going to use this 1273 Kelvin, and we're going to multiply it again by our same delta S. And what we get for this one is negative 24.1 kilojoules per mole. Okay, so that's interesting. So now we have a negative value. So what happened was we indeed had a big enough value for this negative T delta S term to outweigh our positive delta H. So at some point it switched from being non-spontaneous to spontaneous. At what point did that happen, and how do I calculate that temperature at which the spontaneity switched? Well, you might be thinking, well, in order to go from positive to negative, it needs to pass through 0. So 0 must be the switching point, and that's correct. Conceptually, what that means is when delta G is 0, the reaction is neither spontaneous nor non-spontaneous. It's at equilibrium. Well, equilibrium is another topic, but it basically means that the forward reaction is the same rate as the reverse reaction, and it doesn't go in one direction over the other overall. And so that would suggest that it's not spontaneous in either direction, and delta G is 0. So we're going to set delta G to 0 for this next calculation, because we're going to say 0 is the point at which spontaneity switches from spontaneous to non-spontaneous. And that again equals delta H minus T delta S. But this time we are solving for temperature. Okay, so we have got to do some algebra and isolate temperature. So the first thing that I'm going to do is I'm going to add T delta S to both sides of my equation, and I'm going to get out of that T delta S equals delta H. Okay, and then I'm going to isolate temperature by dividing both sides by delta S, so that is going to give me T equals delta H over delta S. Okay, and so now I have an equation that tells me how to calculate that temperature, assuming delta G is 0. And so what I'm going to do is I'm going to put in my values again. So 178.3 kilojoules per mole over 0.159, always being conscientious of those units, kilojoules per Kelvin mole. Okay, and notice how all of these units cross out except for Kelvin, and Kelvin is in the denominator of the denominator, so it's going to end up in the numerator, and it's going to give us the unit that we want. It's always good to check your units to make sure that your calculation makes sense. This temperature, if you do this calculation, you will get 1120 Kelvin. Okay, so that's the temperature at which the reaction is at equilibrium. It's neither spontaneous nor non-spontaneous, assuming that the delta H and the delta S are stable, relatively stable, over that temperature range. Okay, how can I answer this other question? In what temperature range is the reaction spontaneous? So now I'm asking for a temperature range, not a single temperature. How do I set up that calculation? Well, let's think about it. Delta G, we're going to use our equation again, equals equals delta H minus T delta S. This time we want delta G to be less than 0 because we want delta G to be negative. So we're not going to use an equal sign, we're going to use this caret sign, this inequality sign. We're going to carry that inequality sign throughout this calculation. So again, we're going to do a little algebra here and isolate temperature, because temperature is what we want. So we're going to add T delta S to both sides, retaining our the direction of our inequality sign. Okay? Now I'm going to isolate temperature by, again, dividing by delta S. And this time I'm going to keep T on the right because I don't want to confuse myself by turning around my equation, because then I have to turn around the inequality too. So let's just keep it simple. Delta H over delta S is less than temperature. Now I can turn it around if I want to. I'll just do it in another step. So we always want it open to the same side as it was before. So that means the temperature has to be greater than delta H over delta S. And since delta H and delta S are both positive, it makes sense from our initial analysis that the temperature would have to be greater than some positive amount. We need a higher temperature in order for this reaction to be spontaneous. It's not going to be true for every reaction, but for this reaction it is, because we have positive values for delta H and delta S. So let's do this calculation. That means T is greater than 178.3 kilojoules per mole over 0.159 kilojoules per Kelvin mole. And what you get out of that is T is greater than 1120 K. So just a little bit of a different version of the calculation above it. You may have felt rusty about, well, how do I use inequality signs in algebra again? And so this is a good application of that. Just remember that you need to keep it open to the same side it always was open to in your manipulations of the algebra. But basically what we have is a situation where T has to be greater than some value. If I had asked you in what temperature range is the reaction non-spontaneous, well, anything below that, right? So non-spontaneous would be less than 1120 K. Okay, and you could start all over again and turn this inequality around the other direction, and you would get that. Or you can just think about what your answer means. If all of your temperatures above 1120 K are spontaneous, then all temperatures below 1120 K must be non-spontaneous. So that's it. Do a few practices with different reactions. Find the delta H and delta S using delta H as a formation and standard molar entropies, and play around with how to calculate temperature at different conditions for spontaneity, and then also how to calculate delta G at different temperatures. Always assume that your delta H's and delta S's are going to not change too much at different temperatures so that you can do this.